Awesome. Hello, everybody. I'm Chloe Romero. Welcome to my presentation about an infrared camera system that we're using to image a lava lake in Hawaii. So, a little bit about myself. I grew up a very curious kid, like most of us here. So, I was very curious about how things worked. So I'd love to take things apart and see what the mechanics are behind them. Of course, afterwards, those things would never ever make it back together. Taking that same curiosity to who I was then to who I am now. I love mechanical and chemical engineering. Excuse me. What that means is I love building robots and things like solar panels and wind turbines. So academically, that's where my comfort zone lies. So I decided my FSI goal was to really make this a true learning experience, take away new information from this. So I chose volcanology because volcanoes are awesome. So why did we study the lava lake? Well, essentially, the lava lake is a bit of a safety hazard. And it's located in a national park, so they get many, many, many visitors every year. So, and it could potentially just erupt at any time. We don't really know too much about what's going on behind the plume, which I will talk about later. And so this is a potential threat for tourists and the residents there. So a little bit of background about Kilauea, essentially why this is a problem. So it's a problem because as you can see our photo up here, that's a picture of Kilauea on the average day. So what we can't see is the lake. That's what we're trying to look at. And the photo below it is a picture of the lake on a very, very rare day. So standing, I'd say right here on the side of the crater, down in here is the lava lake. The lava lake is probably about the size of a football field. So that's where the team would sit, work, and look down into the lake. And here, this is a picture of a thermal image. So if we're getting pictures from using thermal imaging, why can't we use infrared? So there's a picture of that, the lava lake. Okay, so our project goal, the big overlooking goal for this project is to be able to measure high-speed topography using an infrared camera system. So my lovely little slice of the scientific pie, my goal for this, is to be able to design an experiment to test our camera's capabilities and its filters, which we will talk about next. So a little bit of background about the camera. We're using the average digital camera. We had it converted to see UV through infrared, and we had it equipped with 4 different filters. Now, we have a list of filters, the filters that we have. So we have the 590 nanometer filter, 780, 850, and 1000. So after kind of measuring what we had, we came up with a hypothesis. So what our hypothesis was we think that the 1000 nanometer filter is going to give us the most detail from seeing behind the plume because it's closest to infrared. Now the infrared spectrum starts right here, right after infrared. So the window is small enough for infrared that it should be able to give us a lot more color, and we should be able to measure the level of the lake, essentially. And so that leads us to the question that we get asked most. Why are we not using thermal? The answer, honestly, to that is it's very expensive, and the pixel sizes that we're getting from our thermal images, they're too big. They're too big to give us any kind of detail for the things that we're looking for. So, and then that leads us to our bigger question: Will infrared let us see through the plume? So that's what our project is about: is testing that before we go to the Big Island to get our images and the information we're looking for. So our methods and our process. So we designed and built a plume, the plume machine, as you can see, it's lovely. And this is, we'll talk about this more later. We have a slide for this. So first we took this and we placed it in front of our hot plate. Now the hot plate, you can see it right here on the hot plate. We put rocks on it, mostly to give the camera something to focus on, give the picture more dimension, because the hot plate is white and the plume will be white. So we needed to give some differentiating shades. So originally, the rock that Kilauea is burning is basalt rock. And so originally we were going to use basalt to simulate the lava lake. But it turns out that basalt would take many, many hours to heat through, so we used shale instead to simulate the lava lake. And so as you can see, this is what our setup is like. We have our plume machine, the hot plate, and our camera set up. And this is a picture of the finished product of the plume, which is here. And so after getting everything set up, we took a series of photos with the filters to get to see what kind of results we would get with these. So, yeah, look at that. This is a moment of triumph, knowing that our plume machine works after some bit of worry there. So, how does this work? What is this? This is what is going to simulate our plume, our problem, essentially, but on a very, very smaller scale. So what we did is we took a coffee can, we cut a square in it for a gutter tube. This is going to simulate almost like a chimney, and then on the lid we cut a space for a computer fan. And so inside is where the chemical reaction is happening. We put, I'd say, a 4x4 piece of dry ice and about 2 cups of boiling water. Put the lid on, turn the fan on, and you have this plume here. This is what the reaction looks like. This is how it's designed to work. But testing all of our equipment, we found out that some of our filters and the camera, they don't work indoors. So there's just not enough light, and the filters are very, very sensitive. So we had to problem solve this by taking our experiment outside. And so what we found when we took it outside is that 2 out of the 4 filters will work, but the air isn't stagnant enough, and there was wind, and so the plume was very, very wispy in a sense. So that's the way plume works. Now, our results for our filters. So, like I said, only 2 out of the 4 filters worked, and that was the 590 and 780. These ones worked because their windows weren't as small as the 850 and 1000 nanometer filters. So they were able to let in more visible light, and they reacted a lot nicer to the sunlight and what was happening outside instead of inside. The 850 and 1000 nanometer filters, they need extreme temperatures and a lot of bright light to be able to get any image at all. We tried taking pictures and they came out black. We didn't see anything. So those are some of our conclusive results for the 590 and 780. Now for our temperatures, essentially the basalt that's burning in Kilauea is about 1,000 C, and so we have an average 1,000 watt hot plate, which is going to get about 200 C. So there's a big difference there, but we are working on a much smaller scale. So we did manage to get some kind of conclusive results with these, but they do need further testing, and essentially this entire experiment needs to be enhanced to work better. So for our conclusions, we found that we generated the lava lake, or the plume successfully. The plume, like I said, it works indoors, but not outdoors. So what we're doing to fix that is we're going to go ahead and double everything. Add more pieces of dry ice, more water, and it should enhance the reaction that happens. We haven't had a chance to test this quite yet, but it should work, pretty sure. So our lava lake finding where our hot plate just wasn't hot enough. It wasn't hot enough. That's why we only got results for our smaller filters. So a way that we could potentially enhance this is to get something much hotter, say like a soldering iron or maybe a stovetop. But the bigger filters need more extreme things to focus on for them, in order for them to see. And only 2 out of the 4 filters worked, the 590 and 780. So we did get conclusive findings with those, but not with the other 2 filters. Our next steps in this project are to be able to get those to enhance the experiment, to be able to work all together. All of the filters work, and we get conclusive pictures with all of them. So those are kind of our next steps, and that's how those are our suggestions for modifications in the future for people who would like to look more into this research. Okay, so my acknowledgments. I can't thank enough my mentors for letting me be part of this excellent journey. I loved every part of it. I never knew I'd love volcanoes so much, or cameras. Amy and Dr. Anderson, and of course my advisor, Sean Hoskins, for reading over my papers and whatnot, giving me helpful advice. And I can't thank, honestly, enough for my sponsors. Without them, I wouldn't be here. So I can't thank enough Chesapeake Energy and the Kinder Morgan Foundation. They got me this spot here today from my learning experience. And of course, my friends and family for putting up with my science talks. Okay. Thank you all for listening. Questions?